Dear students, welcome once again to yet another session on econometric methods course. In the last module, we saw two methods adopted to estimate the distributed lag models in practice, namely the Quiax approach to the estimation of DL model and the ad hoc method. In today's module, we are going to continue with our earlier discussion, and so we see the Ullmann's approach to estimating the distributed lag model. Let us see that. The Ullmann's approach was proposed by Ullmann. Shirley Ullmann proposed this approach. Ullmann tries to model the generalized effect pattern. This model is also known as polynomial distributed lag model. To illustrate this approach, I have shown four figures A, B, C and D. A, B, C and D. The first figure shows the pattern modeled in the Quiax approach. B, C and D is the pattern modeled using Quiax approach. Let us take this first figure. In this figure, you have got x-axis as the lag time and y-axis is the effect pattern measured as the magnitude of the coefficients of the lags. So this measures the coefficient magnitude, and this is declining, uniformly declining at an exponential rate. So it is this Quiax approach tries to model the effects which decreases over time uniformly but at a exponential rate. Quiax approach tries to model other effect patterns like the one you are seeing in the B figure. In this, the effect first increases and reaches a zenith and start to decline. So the effect here is first increasing, then declining. If you consider the third figure, C, here first the effect increases and reaches a point, then it starts to decline, and it reaches another point, threshold point, beyond which it starts to increase. So here you have the multiple turning points are there. So the directions are changing more than once in this pattern. If we take this third and fourth figure, the D figure, here the pattern first declines and reaches a threshold, then it start to increase, then it reaches another threshold level and it start to decline. Here also the effect pattern changes direction more than once. So this kind of patterns are modeled in the Ullmann's approach. Ullmann uses a simple theorem in mathematics known as Weierstrass theorem. Weierstrass proposes that any pattern can be approximated by a suitable polynomial of certain degree. So any effect pattern can be approximated with a polynomial in a variable called I. Ullmann proposes to model the effects with two parameters. One is the polynomial degree and length of the lag, that is effect period is also taken into account. So the two parameters Ullmann assumes are the degree of the polynomial and length of the lag. Suppose to explain the Ullmann's approach, for this I have taken the quadratic pattern or the second degree polynomial in I, a variable, and I have also assumed the effect length is 3. So, for illustration, I have taken the quadratic pattern of effect and the effect length as 3. So, let us write the distributed lag function or distributed lag model. Yt is equal to alpha plus beta 0 xt plus beta 1 xt minus 1, beta 2 xt minus 2 plus beta 3 xt minus 3. So, 3 lags 1, 2 and 3 plus ut. So, to understand this, this can be, this equation can be taken as the inventory model, where Yt is the inventory at time t and sales is the time time t is taken as xt. So, you have got the inventory determined by the sales. So, you have got by this model 3 lag lengths, and the effect pattern is taken as quadratic. So, you are taking one by quadratic function beta I, that is the effect size at time I is equal to beta 0 plus a0 plus a1i plus a2i square. So, this is I is a variable of lag time. So, you are supposed to find 4 coefficients. In this case, beta 0, beta 1, beta 2 and beta 3. So, you have got 4 coefficients. They are expressed in terms of a0, a1 and a2. So, let us once this equation is assumed, let us substitute the first coefficient, that is substituting I equal to 0. If you put I equal to 0 in this equation, so a0 plus a1 into 0 plus a2 into 0 square. So, these two terms get cancelled. So, you got a0. If you put I equal to 1, you get the second effect in terms of the coefficients a0, a1 and a2. That is, if you put I equal to 1, it becomes a0 plus a1 into I, that is here 1, plus a2 into I square, that is 1 square. So, if you reduce this, you get a0 plus a1 plus a2. Similarly, you can find, you can substitute I equal to 2, that is beta 2 is equal to a0 plus a1 into I, that is 2, plus a2 I square, that is equal to a0 plus 2a1 plus 4a2. And if you put I equal to 3, you get beta 3 is equal to a0 plus a1 into I, that is 3 here, plus a2 I square, that is 3 square here. So, it becomes a0 plus 3a1 plus 9a2. Substituting these coefficients in the original equation, we will get expression in terms of a0, a1 and a2. So, we are substituting these effect sizes, effects into the original equation. This is the original equation. You are substituting for these coefficients. So, it becomes alpha plus, instead of beta 0, you put a0 xt plus, instead of Beta 1 you substitute A0 plus A1 plus A2, and instead of beta 2 you substitute A0 plus 2A1 plus 4A2. Instead of beta 3 you substitute A0 plus 3A1 plus 9A2. So the expression becomes an expression in terms of A0, A1 and A2 instead of beta 0, beta 1, beta 2 and beta 3. So rearranging these terms in terms of the coefficients A0, A1 and A2, we are collecting here A0 into xt is here, that is the only term with respect to okay, this is only one term A0 as the coefficient, and if you substitute, if you multiply inside, you get another term with A0 as coefficient, that is A0 xt minus 1. Here also you have a term with A0, that is A0 xt minus 2, and here A0 xt minus 3. If you collect all the terms, you get A0 xt plus xt minus 1 plus xt minus 2 plus xt minus 3. Similarly, you can collect all the terms which has A1 as coefficients. You get another expression like this, A1 xt minus 1, that is not taken from here, and you get here another term xt minus 2, and you get here xt minus and the 3 xt minus 3. So you have got the second term, and you have got third expression. Just collect all the coefficients of A2, all the variables corresponding to A2. That is here you have got xt minus 1, and you have got 4 xt minus 2, and you have got 9 xt minus 3. So you collect all this, and you get the third expression. So you can take these as one single variable. Let us assume this as x0t, and let us assume this as xz1t, and let us assume this as x2t, zt, z2t. So then the expression becomes very simple. That is by expression in terms of the variables z's. So you get yt is equal to alpha plus a0 z0t plus a1 z1t plus a2 z2t plus ut. This is taken as the auxiliary equation. So you started off with the main equation in terms of xt's, the auxiliary equations in terms of zt's. The coefficient also differs. In the first the main equation, you have got all the coefficients in terms of alphas and betas. Here you have got alphas and a's. So the main equation is transformed into this equation. So what you have to do is you have to compute the z variables. Z0t is computed as a simple summation of xt, xt minus 1, xt minus 2 plus xt minus 3, and x1t is a weighted average, weighted sum of the variables xt minus 1, xt minus 2 and xt minus 3, and another weighted summation of the xt minus 1, xt minus 2 and xt minus 3 is found for z2t. So these variables are estimated, these variables are computed, and this auxiliary equation is estimated with these computed variables, and estimation will give the values of alpha, a0, a1, a2. So with this coefficients, you can recompute the coefficients of the main equation. For example, this A0, A1 and A2 could be used to find the values of beta 0, beta 1, beta 2 and beta 3, right? Once the values of A0, A1 and A2 is known, then you can find the value of beta 1. So beta 0 is nothing but A0. Beta 2 very simple. You have got weighted sum of A1, A0, A2 and A1 and A2, and beta 3 is also a weighted sum of A0 plus 3A1 plus 9A2. So this coefficients of the main equation is recomputed using the coefficients we obtained from the auxiliary equation. So this is how the Allman's DL model is estimated, and this model can handle any pattern of effect size. So let us summarize the features of Allman's model. The maximum length or lag k must be specified, or the effect length has to be specified in advance in this Allman's approach. And once the k is specified, we have to specify the effect pattern, right, expressed in terms of degree of polynomial in I, let us say here m. So once m and k is specified, z's has to be constructed. The variables z's have to be constructed. So once it is done, you can very easily run this model with the specifications. So unlike coax lag structure, this approach provides a flexible method of incorporating a variety of effect sizes and lag structures. Unlike the coax equation, here we don't have to worry about the presence of yt minus 1, because yt minus 1 creates the term yt minus 1 in the right hand side of the equation, creates some econometric issues like endogeneity and autocorrelation. Both problems is not there in the Allman's model. Another important issue is the number of parameters to be estimated in the main equation. The number of parameters in the main equation is determined by the effect length. If the effect length is sufficiently large, in such cases, this Allman's approach provides a way out. You need not have to estimate all the coefficients, the long, the long list of coefficients that can, taken care of the long effect pattern. Here, it can be handled with sufficiently smaller number of degree of polynomial, because the degree of polynomial is decides the number of coefficients to be estimated in the auxiliary equation, right? So if the degree is very low, the number of coefficients to be estimated in the auxiliary equation will be low. So with that, we can compute the long the large number of coefficients that found in the main equation can be estimated. So this is another good feature of this Allman's approach, because if the number of parameters to be estimated in the main equation is so large, sufficiently smaller degree of polynomial can really reduce the number of coefficients to be estimated in the auxiliary equation. That in turn really helps to avoid the severe loss of degrees of freedom in the main equation. Let us see some two illustrated examples found one in GS Madala, the other one is from Student Man's 4th edition book, Using Econometrics, a Practical Guide. So let us take the first example. This example is taken from GS Madala's 4th edition, Introduction to Econometrics. So this is the equation, this is the auxiliary equation. So you get the auxiliary equation. In terms of z's, just look at this equation. The auxiliary equation is in terms of z's. So you get to know A0, this is alpha, A0, A1, A2. So using this, you recompute the coefficients in the main equation, beta 0, that is A0, beta 1, you take from A0 plus A1 plus A2, and this is beta 1. So you just add these coefficients A0, A1 and A2, you get the value of the beta 1, and you get the beta 2 also. So this is the weighted sum, A0 plus 2 times A1 plus 4 times A2, right? You get beta 2. So you get the value 0.1321. Beta 3 is obtained again by another weighted sum, that is A0 plus 3A1 plus 9A2. This addition you get minus 0.1 0.5394. So from the coefficients of the auxiliary equation, you find the coefficients of the main equation. So this is usually the standard errors of this main equations are obtained from the standard errors of the auxiliary equations, right? This is with simple a formula from the statistics, you can get this. So this model is got, right? If you see this this pattern, actually this is a concave effect pattern, and concave from the origin, and you get this effect pattern. Let us take another example. Actually, this example is taken from Student Man, the book Using Econometrics, a Practical Guide, and this one you've got to know effects. AT minus 1. Actually, this is a variable, and this is the effects. And so in this one, the first effect increases, and it reaches a highest point, a threshold point. Then it start to decline. Actually, it goes up, and then it start to decline. So this pattern is another inverted U pattern. So this is estimated results of such DL model using the Ullmann's approach. So with this we can conclude the discussion on the Ullmann's model, or Ullmann's approach to the distributed lag model estimation. Let us summarize what we have learned in today's module. I discussed the Ullmann's approach to distributed lag model estimation, how the parameters of model, namely lag length and degree of polynomial, is assumed, how the coefficients of the DL model is estimated from the auxiliary equation. Then I compared and contrasted this approach with other approach, namely the coax approach, and I concluded this session with an example. In the next module, I am going to rationalize the coax transformation. So we'll see in the next module. Until then, goodbye.